Welcome to Organic Chem 320. And the first video of the semester is going to deal with hybridization. Alright, so what you're going to learn from this video is how atomic orbitals combine, what are the three different hybridization states of carbon, and what atomic orbitals combine to give you Sp3 hybridized carbons, Sp2 hybridized carbons, or Sp hybridized carbons. Alright, we're also going to discuss how hybridization affects electronegativity toward the end of the lecture. Alright, so we talked already about Sp3 hybridization, and we said this happens when 1s and all three p orbitals add together or combine to give you 4 Sp3 hybrids. So if you had to think about this in terms of mixing or addition, remember these orbitals are equations. Okay, so if I were to take my orbitals here, my 1s and all three of my p's, and if I had a machine, we'll call it a hybridizer. This is what would happen. So the orbitals will go into the machine. There would be some action, and then my four hybridized orbitals come out. Notice I added 4 atomic orbitals together, and I now have 4 hybrid orbitals. And then let's keep in mind also the size of the lobe in the hybrid is you can kind of relate that back to the sign of the equation. Okay, so if the two signs were equal, or the two signs of the equations matched, like for the S and for the P, then that means that you'll get a larger lobe for the equations that have matching signs. Alright, so let's keep going. We have not discussed Sp2 hybridization, so let's get into that now. Alright, so with Sp2 hybridization, you have an S, and then you have 2 of the p orbitals to give you 3 Sp hybrid orbitals. So let's take our S and our 3 p's and let's put them in the hybridizer. Let's see what happens. Right, and so notice we have 3 hybrids because we added together 3 atomic orbitals. And we have 1 unhybridized p orbital, which in this case would be Pz. So I know you're asking, where is Pz? Pz is actually here, perpendicular to the plane. So the unhybridized p orbital is just pointed perpendicular to the 3 Sp2 hybrids that are shown here. And when a carbon is Sp2 hybridized, it has trigonal geometry with a 120-degree dihedral angle. So let's go to the next hybridization state, which is Sp. Okay, so if a carbon is Sp hybridized, you can imagine that I'm taking 1s and 1p, right? I'm adding those two together to give me 2 hybrids, right? This is one lobe of the one hybrid. This is one lobe of the other hybrid. So let's put our orbitals here into the hybridizer, mix them up, and then what you see is now I have 2 Sp hybrids and then 2 unhybridized p orbitals. So where are Py and Pz? They're here, right? Py is here, pointed straight up and down, and Pz is here, pointed along the z-axis. So we've already discussed how to make hybrid orbitals, right? You take an S and a P in this case, and you add them together, and you get an Sp hybrid, which is shown here on the screen. For Sp3 hybridization, what you'll notice is that you're adding together 1s and all 3 p orbitals to give you 4 hybrid orbitals. Those 4 orbitals are shown here on the screen. When those 4 orbitals combine, that's how carbon is able to form the tetrahedral geometry that you see here. Alright, notice the bond angle is 109.5, and every carbon that's Sp3 hybridized has a tetrahedral geometry. When we're dealing with Sp2 hybridization, you're combining 2 of the 3 p orbitals and the 1s orbital that's in the second energy level to give you 3 Sp hybrids. Alright, and so that's what we have here on the screen. And then those hybrids combine to give you three Sp2 hybrids, which have a trigonal geometry, and then the unhybridized p orbital is shown here in red. That's the p orbital that's going to overlap with another unhybridized p orbital to give you a pi bond. Okay, so we've discussed sp3 and sp2. Now let's look at sp hybridization, where you take the s orbital, the 2s orbital, and one of the two p orbitals, and combine them, and you get two hybrid orbitals shown here. Notice pz and py are unhybridized, but when we combine those with the two hybrids, this is what an sp hybridized carbon would look like, with the two green lobes being the hybrid orbitals, and then the two red lobes here and here being the unhybridized p orbitals. So here's some examples of the different hybridization states that we've been talking about. So this molecule here is ethane. The carbons in this molecule are sp3 hybridized. Notice that all sigma bonds exist in this molecule, and the carbon-carbon bond results from sp3 overlap. And so one of the things to remember here is this. All right, so for a carbon that's sp3 hybridized, it has four groups attached to it. So you have one, two, three hydrogens on this carbon, and then you have this carbon here, which is the fourth group, and then the same goes for this carbon. All right, so if you want to easily recognize a carbon that's sp3 hybridized, or any atom that's sp3 hybridized, one of the things to remember is that that atom is going to have four groups attached to it. All right. The second example here is an example of an sp2 hybridized carbon. Notice now we have a double bond. That double bond is composed of one sigma bond and one pi bond. All right. The sigma bond comes from the two sp2 hybridized carbons overlapping through the two sp2 hybrids, and then the pi bond comes from overlap of the unhybridized p orbitals that we've talked about earlier. All right. Now let's look at this example. This is an example of a carbon that's sp hybridized. Notice there's a triple bond. That triple bond is made up of one sigma bond and then two pi bonds. All right, and the carbons in the triple bond are sp hybridized, and that one sigma bond comes about because of sp-sp overlap. So the sp hybrid on this carbon overlaps with the sp hybrid on this carbon. All right, and then the two pi bonds come about because of overlap of the two unhybridized p orbitals that exist for an sp hybridized carbon. The last thing that we're going to discuss in reference to hybridization is the effect of hybridization on electronegativity. So what you'll notice in the table here, we have sp3, sp2, and sp as the three different hybridization states. And sp3, if we think about all four of the orbitals that added together being equaling 100%, 25% of those orbitals would be s, and then the other 75 would be p. Right, so an sp3 hybridized carbon is 25% s character. Right, and then an sp2 hybridized carbon, you can, if all three had to add to 100, then one part of that would be 33%. Right, so sp2 hybridized carbon would be 33% s, and then the sp would be 50% s. Right, and what you'll notice here is the trend for electronegativity. Right, the sp3 hybridized carbon is less electronegative than the sp2 hybridized carbon, which is in turn less electronegative than the sp hybridized carbon. So of all of the hybridization states of carbon, when carbon is sp hybridized, that's when it's the most electronegative. And there's a reason for that. Right, as s character increases on the carbon, what happens to the atomic radius is it shrinks. So the atomic radius decreases, and as the atomic radius decreases, if you remember from general chemistry, the nucleus has protons and neutrons in it. So the protons, or the positive charge in the nucleus, right? Because the nucleus is positive, and then the electrons that surround the nucleus are negative. If the radius decreases, that means that that nucleus is now more exposed, and so the plus charge in the nucleus, if the atomic radius is smaller, that means the plus charge in the nucleus is more exposed. And then you know that that plus charge is looking for something with a negative charge, and in this case an electron. So it's more attracted to electrons, and therefore we see increased electronegativity for sp hybridized carbons because of the decrease in atomic radius. So let's recap really quickly. We talked about hybrid orbitals being a combination of atomic orbitals. We talked about hybridization falling under the concept of molecular orbital theory, and talked about how different combinations of s and p orbitals can give us different hybridization states, right? And there are three hybridization states for carbon: sp3, sp2, and sp. And carbon is not the only atom where you can describe hybridization. I'm just keeping it in terms of carbon for the class. We'll talk about other atoms that can be that have sp3 hybridization or sp2 or sp hybridization when we get to class. The electronegativity, we talked about that. It increases as the percent S character increases. All right, so that's it for this video. If you have any questions, you can send me a tweet, you can email me, or you can just come by the office. All right, peace.